In this video, we'll be learning about what are parametric equations and how do we use them. Imagine that a particle moves along the curve c shown in this figure. It is impossible to describe c by an equation of the form y is equal to f of x because c fails the vertical line test. But the x and y coordinates of the particle are functions of time, so we can write x is equal to f of t and y is equal to g of t. Such a pair of equations is often a convenient way of describing a curve and gives rise to the following definition. Suppose x and y are both given as functions of a third variable t. T is called a parameter. Each value of t determines a point x, y, which we can plot in a coordinate plane. As t varies, the point f of t, g of t varies and traces out a curve c, which we call a parametric curve. The parameter t does not necessarily represent time, and in fact, we could use a letter other than t for the parameter. But in many applications of parametric curves, t does denote time, and therefore we can interpret x, y is equal to f of t, g of t as the position of a particle at time t. Now we must adapt our previous methods for finding tangents for curves of the form y is equal to f of x and apply them to curves given by parametric equations. To find the slope, dy over dx, we take the derivative of y with respect to t divided by the derivative of x with respect to t. When finding the second derivative, you're actually doing d over dx times dy over dx, but with parametric equations, you're doing d over dt of dy over dx all over dx over dt. Now let's look at how we actually got to these equations. If we substitute x is equal to f of t and y is equal to g of t in the equation y is equal to f of x, we get g of t is equal to f of t. And so, if g, uppercase f, and lowercase f are differentiable, the chain rule gives that g prime of t is equal to f prime of t times f prime of t is equal to f prime of x times f prime of t. If f prime of t is not equal to 0, we can solve for f prime of x. That means f prime of x is equal to g prime of t all over f prime of t. Now we would also like to know how to get to the second derivative of y with respect to x. It is important to remember that the second derivative is not equal to the second derivative of dy over dt over the second derivative of dx over dt. It can be seen from the equations we just derived that the curve has a horizontal tangent when dy over dt is equal to 0, provided that dx over dt is not equal to 0, and it has a vertical tangent when dx over dt is equal to 0, provided that dy over dt does not equal to 0. This information is useful for sketching parametric curves. Here's a question to practice what we just learned. If a curve is given by x is equal to sine of t and y is equal to cosine of t, what is dy over dx? Pause the video so you can do it on your own, and then look at the answer. Let's walk through it. First, we need to find the derivative of y and the derivative of x. The derivative of cosine of t is equal to negative sine of t, and the derivative of sine t is equal to cosine of t. So then we put negative sine t over a cosine of t, and we get negative tan of t. Now let's move on to something slightly more difficult. Parametric equations are given by x is equal to 2 plus secant theta and y is equal to 1 plus tan theta. Find dy over dx and the second derivative at theta is equal to pi over x. Please take a moment to pause the video and do it on your own. The derivative with respect to t of 2 plus secant theta is equal to secant theta tan theta, and the derivative of y with respect to t is equal to 2 secant squared theta. When we put 2 secant squared theta over secant theta tan theta, one of the secant thetas cancels out from the top and bottom, and so we're left with 2 secant theta over tan theta, which then cancels out, and we get left with 2 over sine theta. Now we input pi over 6 in place of theta, and we end with 2 over 1/2, which is equal to 4. Now using the formula of the second derivative, we know that if we find d over dt of the first derivative, all over dx over dt, we'll get the second derivative. So we take what we got in the last problem, which is 2 over sine theta, multiply that by d over dt, and put it all over dx over dt. And here's what you get. You end up with negative 2 cosine cubed theta over sine cubed theta. To finish out the problem, we replace theta with pi over 6, and the cosine of pi over 6 is root 3 over 2, and the cosine of pi over 6 is 1/2. So we get negative 6 root 3. Velocity vectors have an x and y component just like parametric equations do. And so it can be represented as f prime of t and g prime of t. Velocity can be expressed as the square root of dx over dt squared plus dy over dt squared. Now let's look at a problem with an object in motion with the parametric equations of x of t and y of t. The length of the curve determined by the equations x is equal to t squared and y is equal to t from t is equal to 0 to t is equal to 4 is. We can use the equation we found to find the velocity to find the length of the curve, except we're going to take the integral. dy over dt is going to be equal to 1, and dx over dt is going to be equal to 2t, and the integral will range from t is equal to 0 to t is equal to 4. We input these all into the equation, and there we have it. So for part A, we know we have to find the derivative of x and the derivative of y, both with respect to t. We get 2t to the power negative 3, comma negative 2t to the power negative 3, and then we input t is equal to 3, and you get 2 over 27, comma negative 2 over 27. That's our acceleration vector. For part B, we start off by doing antiderivatives, where we get the vector of r is equal to t plus 1 over t plus c1, where c is the constant that we need to find using the initial condition. And for the y, we get 2t minus 1 over t plus c2. It's already given to us that the position of the particle at time t is equal to 2 comma 6. So we use that and we get t plus 1 over t for x and 2t minus 1 over t plus 5. And then we just input at t is equal to 3 and we get 10 over 3 comma 32 over 3. When it says the velocity vector at any time t is greater than 0 is given by 1 minus 1 over t squared, comma 2 plus 1 over t squared, we're actually getting dx over dt, comma dy over dt. So since 8 is equal to dy over dx, we just input the equation dy over dt over dx over dt, and then we end up getting t is equal to square root of 3 by 2. Now we take the limit as t approaches infinity of dy over dx, and 1 over infinity it gives us 0, so we get 2 over 1, and that equals 2. So the slope of the line is equal to 2. When finding the speed, we find that dx over dt is equal to the sine inverse of 1 minus 2e to the power negative 2, which you get is equal to 0.817. Then we find dy over dt is equal to 4 times 2 over 1 plus 2 cubed, which is 8 over 9. And the velocity vector is found using the equation square root of dx over dt squared plus dy over dt squared. And when we input all the values that we just found into that equation, we get 1.208. To find the acceleration vector, we need both components. So we find d over dt times dx over dt, and we get 1 over square root of e to the power t minus 1. Then we do d over dt times dy over dx, and we get negative 4 times 2t to the power of 3 minus 1, all over t cubed plus 1, all quantities squared. And you get 0.396, comma, negative 0.741. Part B is asking us to find what is t when we're looking at dy over dx when dx is equal to 0. So in this case, we're going to set it equal to 0, and then we find t is equal to ln 2, which is equal to 0.693. M of t is equal to dy over dt times dt over dx, and then we take the limit as t approaches infinity, and we find that it is equal to 0. Since the limit as t approaches infinity of x of t is equal to infinity, c is equal to the limit as t approaches infinity of y of t, which is equal to negative 3 plus the integral from 2 to infinity of 4 of t all over 1 plus t cubed dt. Thank you for watching this video on parametric equations.